I want to talk to you now about confidence intervals. So hypothesis testing is, you've almost certainly seen this used and it quoted, even in, so I was trying to think if I see it in newspapers, you certainly see it in any sort of semi-technical press. Confidence intervals you probably have seen as well. They're sort of pairs of numbers with squares round, which are giving you some idea of the range that something's in. So they're about bounding your uncertainty by giving a range. Now we talked about the fact that when you've not found something significant, you can't say therefore there was no difference, or therefore between them. So you've got your new system, class thing, system B that you've designed, system A that is the old one. You haven't found a significant difference. Does that mean that they're no different? Or does it just mean your experiment hasn't been good enough to show that they're different? Now, if the only reason that you might want to deploy system B is because you think it's going to be better for people, then it actually, if you're not showing a difference, you either still need to do some more work on that, but or you might just decide to do some more work to just improve the system. So that if there's going to be a difference, you're going to want to make it a nice big one. However, it can be worse than that. Imagine there's some other reason. Perhaps it's just going to be more robust. It's going to run on cloud infrastructure or something like that. You really want to be sure that system B isn't worse than system A. Right? So there's proving it's better and proving it's no worse. And certainly if you're going to start deploying it, it's one thing not being 100% sure whether it's better, but well, might as well. But it could be worse if it could actually do damage, even if it's got some other advantage. So you really want to know about this sort of stuff. So you've not got a significant result, but that just tells you your maximum experiment wasn't good enough, right? The real difference might just be smaller. So you can't, so in one sense you can never prove equality because you're always going to get tiny differences that do things. What you can do is put some bounds on inequality. How different are they likely to be? How small and narrow is that? And a confidence interval does that. I mean, it doesn't just do that for when there's no effect, it also does it for when there is effect, to say bounds on how big an effect is. But it's particularly important, I find, particularly when it's in that region where you're trying to show something is nearly equal. So it uses the same theoretical and methodological ways of dealing stuff as hypothesis testing when you get your P. But instead of saying, doing that, is it true or is it likely to be true type test, it's saying what are the bounds on it. So imagine we've done some tests, we've done some response time tests on system B. So imagine system A, our average was a 2.8 second response time for something or other, and system B was a 2.5 second response time. It was faster. So the mean difference was 0.3. Right, so if you took system B time, system A time minus system B time, 0.3. So system B is 0.3 on average over our tests, was coming out 0.3 seconds better, about 10th of a second, a 10% improvement on your sort of 3 second-ish time. Yay! Okay, is that good? You might have done your stats and didn't get a significant result. So what you do is you plot or you ask your package to tell you your 95% confident interval. And you can ask for a 99% or 99.9% one, which tend to be wider. If you want to be more sure about the range it's in, you tend to get a bigger range. So if you say, oh, I don't care too much if it's outside the range, just give me a sort of vague idea, 95. If I want to be pretty sure it's inside the range, the more sure you want to be that it's inside the range, the bigger the range is, because the range is giving you that sort of measure of how uncertain the results are. If you've seen your error bars on graph, they're actually not a confidence interval, but you can plot confidence intervals, but they're doing that, giving some measure of the range of certainty. So imagine I've done my 95% confidence interval, I've asked my stats package for this, or you've worked it out from first principles and you're in Excel or something, and it said it's minus 0.7 to 1.3. All right, this is for the difference between the two. What that says is if the real value isn't in that range, then the probability of seeing the data you've got is less than 5%. Now this is starting to sound similar, and it is similar to the hypothesis testing. So let's give an example of that. So say, so what we've seen is the average, on average, we've got system B 0.3 of a second faster than system A in terms of response time. The upper bound on this was 1.3. So imagine actually system B was 1.6 seconds faster on average. Really, if we'd had thousands and thousands of users and we could deploy it fully. So imagine if really it's actually fast. It's just that people vary a lot on our experiments. We just happened to get, maybe it came out as low value just because when people were doing system B, they just didn't do as well, right? So there's reasons why it might not have turned out like that way in the experiment. But imagine if the real value was 1.6 seconds. What the confidence interval tells you is that the likelihood of seeing the measurement you've got, given that 1.6 seconds, is less than 1 in 20. Similarly for 1.5 seconds, 1.4 seconds, 1.31 seconds. On the other side round, it says, what's the likelihood of, say, system A actually being the faster one? Right? So we saw that system B was 0.3 a second faster than system A, but the confidence interval has a negative one as well. So it could be, that's sort of saying the minus 0.7 to 1.3 is saying somewhere between system A being faster than by 0.7 and system B being faster by 1.3. So although the average that we got out of measuring these was 0.3, it could be quite a lot faster than that, but it could be not only less good than, not as much as an improvement, but actually it might actually be slower than system B, so system A. So what this though says on that side is equally, it says it on the positive side, but on the negative side it also says, well, imagine if system A was actually a whole second faster than system B. Our new system is actually slower by a second. The likelihood of seeing our measured results given that, less than 1 in 20. Similarly for 0.9 seconds, system A being 0.9 seconds faster, or system B being slower, or system B being 0.8 seconds slower, or 0.7136 seconds slower. So it's saying that anything outside that range, the likelihood of seeing the experiment results, if any of those were true, is less than 1 in 20. Inside the range, it varies what that likelihood is. So again, this is a counterfactual argument. It doesn't say, and probably the next slide will say this, it says it's a counterfactual argument. So when you've got the 95% confidence interval, it's not saying there's a 95% probability that's in the range. And this is very like the statements we've said about the significance testing. It either is or it isn't. So, if the system were run on every user ever there was, one of them is faster than the other. Right, or they're absolutely the same. There's not a probability of it. It either is or it isn't. All it's doing is saying that if system A were faster by a certain amount, inside or outside of this range, or slower by a certain amount outside of that range, then the likelihood of seeing the results is less than 1 in 20. If you go for a 99% range, it's the same, but it's saying that things outside that are less than 1 in 100 chance of seeing the results. So that's a more solid result, but you end up with a bigger range because you can't be as sure. Now, these, of course, having this right, it's forget the to some extent the philosophy of it. What this is doing though is giving you a much solider idea, rather than just saying it's not different. Or, rather than saying, I can't prove that it's different, you're saying the difference is within these bounds. It's even stronger than when you have got your lovely 5% or 1% significant result, right? And you say, I've got a significant result. And the average is, well, the confidence interval doesn't say just where the average is, it says, and the real result is likely to be in this range. It gives you a range, not just the middle value. So going back again to these issues, if you've done your experiment, we had our experiment result, system B was 0.3 seconds faster, it was not significant, oh, we've got nothing, nothing, not proven, but you do your confidence interval and it says it's somewhere between, or it's likely to be, so you have a reasonable level of confidence that it's no worse than 0.7 seconds slower than system A, but also probably not more than 1.3 seconds faster than system A. Now, my original example, I think I gave 2.8 seconds, or so some fastish response time thing versus 2.5. But imagine this was over a 5-minute interval, something more like 5 minutes. So say, imagine it being 280 seconds for doing a big task for system A, and system B was 279.7 seconds, 0.3 seconds faster than system A, right? And we have the same confidence bounds. 1.3 seconds, do we care? So if it's a matter of the reason why, if system B was going to be costly to deploy, and the reason we're deploying it is because we think it might be better, and we've just got these results, to be honest, would you bother? I mean, sometimes that tiny little percent makes a difference, right? If, though, the issue is we want to deploy it for all sorts of other reasons, is it going to make things worse? Then the minus 0.7 starts to kick in. It could be up to 0.7 seconds slower than system A. Does that matter? Well, if you're talking about that over a 3-second response time, yeah. If you're talking about that over a 5-minute period, who cares? So whether it's an important difference or not is a question you have to answer. What the confidence interval gives you, though, is how likely it is to be within a range. Then you can look at that range and say, do I care? Is that important? And make your decisions based on that. So, I hope you got some idea of what a confidence interval means and why it's useful. Put more in the notes on this. A few things to say, though, and this is actually, the first is more for if you're publishing this as a piece of science. The second, perhaps, for practical uses. Well, for science as well, actually. The first is, if you write this down, if you put it in your company report, if you put it in your CHI paper, do remember to say the same things that you would if you'd been doing traditional hypothesis testing statistics. So when people do their comparison, put their P, they will tell you things depending on your knowledge may or may not make more sense, but they'll tell you what distribution they were using. Is it the student's t-test? Is it a ANOVA? What were they using? Is it for coin tossing? It would be a binomial distribution. What's the distribution? What are the degrees of freedom if you're fitting things? Perhaps working out, so for instance on 2 measures, we're ignoring how big the overall size of something is. We fitted numbers of factors to something. How many degrees of freedom? There's all these things. You normally just see these things called how many people there. Now I mention that because I have seen papers where they've quoted a confidence interval because they've read that there's all sorts of problems with traditional statistics testing, and confidence intervals are good, which they are good, very good. So they've quoted their confidence interval, but they haven't told you the things that you would normally expect to see, because they sort of think, oh, it's a magic confidence interval, and they're not used to seeing them. So if you're going to quote it, do quote all the same things around it. The other thing to remember, though, is although you're getting these bounds, it is still uncertain. Everything you get from statistics is uncertain knowledge. It's not saying absolutely definitely it's in that range. It's saying it's quite likely to be in that range. If it was, and strictly, all it's saying is if it was outside the range, the results we saw would be highly unlikely. But it might still be. It might be that you got that result out of the range and you just got a fluke in your experiment or in your study. So you still, in every bit of statistics, it seems, and I think the danger of the confidence interval is because it's giving you the bound, it perhaps gives you a bit more, and it does give you more understanding of what's going on, but you might overbelieve in that. it is still quite possible, albeit unlikely, that it's sitting outside that range.